Section 1.1, question 9. Let G equals the set of elements of the form a plus b root 2 in the real numbers where a and b are rational. This is a nice example that you would probably see in algebraic number theory. Prove that G is a group under addition, and prove that the non-zero elements of G are a group under multiplication. And the hint that they give is to rationalize the denominators to find multiplicative inverses. So let's see how we can do this. First, we're going to see how to prove that this set forms a group under addition. So as usual, we observe whether or not it is closed. So if we have a plus b root 2 and we add c plus d root 2, it becomes a plus c plus b plus d root 2. And since a and c and b and d are rationals, their sums are also rational. So again, we have something of the form rational plus rational root 2. So obviously closure is satisfied. Associativity, we can easily check it. Calculation is a little bit long, but let's try. A plus b root 2 plus c plus d root 2 plus e plus f root 2. So we want to check the addition of this first part plus e plus f root 2 at the end, and then see that it is the same thing as a plus b root 2 plus this second part. You can guess that associativity is going to hold, largely because of the associativity of addition in the reals and addition in the rationals. But just to check what the outcome is going to be, we can see that this one is going to end up being a plus c plus e plus b plus d plus e root 2, and this one is also going to give a plus c plus e plus b plus d plus e root 2. Oh, and I made a mistake because these e's should be f's. But we can easily see associativity from there. So now what about inverse and identity? Clearly, if we want identity, we can take 0 plus 0 root 2, because if we were to add that to sum a plus b root 2, we just get 0 plus a plus 0 plus b root 2, which is the same thing, a plus b root 2, that we had to begin with. If we reverse the order of addition, it will be the same thing. And what about inverse? A plus b root 2. Well, we're looking for two elements that will make a and b 0 when they get added. So we can pick minus a plus minus b root 2, which will give 0 plus 0 root 2. So we can see that this suffices for an inverse, and since a and b are rationals, minus a and minus b are also rationals, so the inverse definitely exists. Thus, we have proven that the set of all numbers a plus b root 2 in R, where a and b are rational, they form a group under addition. The second part, we want to talk about multiplication, and we're only restricting ourselves to the non-zero elements of this set. So we won't be considering this element here as part of it. So to test what that multiplication is going to look like, take a plus b root 2 and just do the usual multiplication, expanding the brackets. So that's just a, this is c plus d root 2 plus b root 2 into c plus d root 2. That gives us ac plus ad root 2 plus bc root 2 plus 2bd, which is ac plus 2bd plus ad plus bc root 2. This is rational, this is rational, so clearly it has the same form when we do this sort of multiplication, and we have closure. So we only need to care about identity and inverse. Observe that if you take 1 plus 0 root 2 and multiply it by a plus b root 2, we get 1 times a plus b root 2 plus 0 root 2 times a plus b root 2, which gives us a plus b root 2. So clearly this element of the form 1 plus 0 root 2 functions as our multiplicative identity. Now we need to find the inverse. So we want some element that you can multiply by a plus b root 2 that would give you back the identity. How do we get that? Looking at it, we can see that a plus b root 2 times 1 over a plus b root 2 will give us back 1, which is the same thing as 1 plus 0 root 2. But we need to get this element in the form something plus something root 2, where this m and n, these somethings, are rational. So we're going to do this rationalization by using conjugates. So a plus b root 2 times a minus b root 2 divided by itself. And this works because this side is actually just equal to 1, but it's in a convenient form. So what we're going to have is a minus b root 2 divided by a squared minus 2b squared. And in fact, this element works as an inverse, because if you take a plus b root 2 and you multiply it by this element, a minus b root 2 divided by a squared minus 2b squared, we get a squared minus 2b squared divided by itself, which is 1, which is the same thing as 1 plus 0 root 2. And there we have inverse and identity, and we already have closure. But what about associativity? That's the last one. We need to show that a plus b root 2 times c plus d root 2 times e plus f root 2 is the same thing as a plus b root 2 times c plus d root 2 times e plus f root 2. And in order to verify associativity, we just need to make sure and perform these two multiplications, expanding out the brackets, and make sure that they result in equal expressions, the same expressions. And that will conclude the proof that the set of the form a plus b root 2, where a and b are rationals, except for the 0 element, 0 plus 0 root 2, under multiplication is a group.